In this lesson, we're going to be looking at graphing some of the rational functions we've been looking at recently. So we want you to be able to determine the undefined values, and we'll talk about those in a little bit. Those are the vertical asymptotes and the holes of any rational function. So looking at some of those graphs, you're going to see something different than what we've had in the past. So far this year, you've looked at linear lines. Those are any lines where you have a constant slope here. We've looked at quadratic ones. Okay, quadratic are any in the form y equals ax squared plus bx plus c, whereas linear lines we know is y equals mx plus b. Square root functions we've looked at. Those are anything with a square root involved. And we've looked at some other polynomial functions in previous units. But now that we have rational expressions, you're going to see some different things happen. This first word problem says a group of students want to get their favorite teacher, Mr. Domingos, a birthday gift. They plan to get him a gift certificate for a weekend package to a lodge at a state park. The certificate costs $150. If C represents the cost for each student and S represents the number of students, then our equation would be to get this the $150 they have to pay divided by the number of students here, which would be S. So whatever we get when we take 150 divided by S, that would be the graph. If you were to then go over and graph this out, you would get a graph that looks something like what we have up here. Okay, the cost for 0 students, we would not be able to do, since 0 is not, you can't put 0 students in here and pay for it. So that's why you see this graph keep kind of going up here and increasing forever. Okay, so that is not possible. So what we would say here is that 0, S equals 0, 0 students is not in the domain. Okay, and what we're going to get there then is at 0, there's like an imaginary line here that our graph gets closer and closer to and never touches. As we'll see in a second, that's called an asymptote. Okay, so that it means our graph is going to keep approaching that line. So we could have one student. If one person paid for it, they would have to pay all $150. And any combination in between would also work. If there were 25 students, then each of them would pay $6 and so on. So you could just take whatever 150 is divided by the number of students, and that would be the cost. If 150 students did it, 150 divided by 150 would mean it costs $1 for everybody. So this graph shows the different combinations that would work. This is different though because we get this imaginary line involved called an asymptote. So you're going to see asymptotes pop up in our graphs. Okay, so rational functions. This is in the terms that you can write in here. A rational function is a ratio of 2 polynomial functions. So you got one on top, in this case P, function P, and then one on bottom, function Q. And because you're dividing, there is going to be some things then that you can't divide by, because we remember you can't do division by 0. So in this function F here, there's a value that we would call undefined. Undefined means that the value, you can't put that number in because we can't calculate it out. And in this one, it would be x equals -3. Because if we were to put -3 right here, -3 plus 3, that's 0, we can't have dividing by 0. Even though we got a -3 on top, we can't divide that by 0. The way you can find all these undefined values is to put anything in the denominator equal to 0. So like on this next one, if we put x minus 6, the denominator equal to 0, and solve it by adding 6, we see that x equals 6 is the domain restriction for that one. X can't equal 6 in this problem. Just like in the last one, x cannot equal -3. So for function h here, this one looks like it's going to have 2 of them. If we put x minus 1 equal to 0, that means we get x equals 1. X cannot equal 1 here, because if we put 1 in for that x, that's 0, and you get division by 0. The other value would be -4. X can't equal -4 because you'd also get division by 0. So domain restrictions, or where it's undefined, is anything where you get division by 0. Okay, another term you're gonna hear, continuity. Continuity means the graphs of rational functions may have some breaks in the continuity. You won't be able to trace the graph without picking up your pencil. Breaks that occur at values that are excluded from the domain. Those are those undefined values. Okay, so using the examples from above, the places that it would not be continuous at, f would not be continuous at -3. That would be for function f. For function g, the restriction would be right there. For g, you couldn't have x equal to 6. And then the same thing for h would have 2 values from above. All right, some other terms here that you should know. Vertical asymptotes. Okay, those are going to happen anywhere that you have division by 0. Okay, so a line, it's a line that the graph approaches but never touches. So here is an example right here. You can see this dotted line on the graph. That is our vertical asymptote. It looks like it's at x equals 3 is where this asymptote is. So this one has an asymptote at x equals 3. And the reason that it's there is because in the denominator here, if you put 3 in, you get division by 0. So that means our graph is going to get closer and closer and closer to this line, but never actually touch it up here. And down here, it's going to get closer and closer, but never touch it down there. One last term is point discontinuity, or we also call those holes in the graph. Holes occur when you have a value excluded from the domain, but also it actually like cancels out with the top. So if you look at this graph, here's the function for it. Notice that in the bottom there is a x plus 2 here. Okay, x plus 2 is in the denominator, which means x plus 2, if we put that equal to 0, -2, there is no value at -2. It's undefined at -2. Okay, this is where it's undefined. But it's not an asymptote. And the reason that on this one it doesn't become an asymptote is there's also an x plus 2 on top. So those values actually kind of cancel out. And so there's no asymptote. And really this graph becomes what's left over. It becomes the graph y equals x minus 1, the part remaining after we cancel out. If you look, we know what this line looks like. It's a linear line that starts at -1. The slope's up 1 over 1. You can see it goes up 1 over 1, up 1 over 1, and so on for the slope. But the difference is that one point, it's undefined there. We don't have a value. That's why you see here there's a hole at -2. If you move this down here, there's a hole right here in the graph that we don't have a value for. And that happens because of that undefined value. So when it cancels with the top, it's not an asymptote, it becomes a hole. All right, so we're going to look at doing some of these. Keep in mind that no denominator in a rational function can be 0 because division by 0 is not defined. So you're looking for the places where the denominator is 0. You can't divide by 0. All right, so now number 1, we want to determine the equations of any vertical asymptotes and any holes for this function. So the steps, first thing we're going to do is factor. What does this look like if we factored it out? So it looks like both top and bottom factor on this one. This top is a difference of squares. That'd be x plus 1 times x minus 1. The denominator is the quadratic, and it factors to 2 binomials. We want to figure out what multiplies to 5 and adds a -3. Looks like, sorry, this one's going to be plus, sorry, looks like, I think they're both negative here, -5 and x minus 1. Okay, So we factored it out. That's the first step. Next, identify all those undefined values. So let's see where this one is undefined at. And it's undefined anywhere you have division by 0. So we want to take the things in the denominator, x minus 5 here, and the other term is x minus 1, and set them both equal to 0. And what we end up with is at 5 and at 1, it's undefined. Those two places, the graph won't have a value at those two places. If you were to graph this on a calculator, what you would see is that when you look up the table on these ones, at both 1 and at 5, it wouldn't have a value. It would say undefined for these two. There would be no value in there. The other ones would all have some kind of number associated with the other ones, but on those two, you'd see it's undefined. So now we got the two numbers. We just got to figure out what's happening at those two numbers. Are they going to be asymptotes or are they going to be wholes? Okay, and how you tell is to look at the equation and look at the numerator. If any of the two things in the bottom cancel out with the top, then it becomes a whole. Well, it looks like this x minus 1 does cancel with the top. Okay, that means this value x equals 1 is a whole. There's a whole at 1 in this graph. This other one, x minus 5, does not cancel with the top. If it doesn't cancel with the top, then it's an asymptote. And it is possible to have more than one asymptote or more than one whole in a graph. So x equals 5 is an asymptote, x equals 1 is a whole. All right, let's try another one of those. On number 2, they want us to determine any ones on this one that would be wholes or asymptotes. So let's do the same thing. Factor it first. So if we factor the top, that's a quadratic. It looks like our two binomials here would be x plus 4 and x plus 2, because 2 times 4 is 8, 2 plus 4 is 6. On the bottom, that's a difference of squares, x plus 4, x minus 4. Okay, so let's start. Where is this undefined? It's undefined anywhere that the bottom equals 0. Okay, so set the two things equal to 0 and see what you get. And if we do that, we get negative 4 and positive 4. So those two values are not in the domain of this one. Okay, what are they then? Are they wholes or are they asymptotes? Well, let's see. Did either of these two cancel with the top? Yeah. The x plus 4 and the x plus 4 on top and bottom cancel out. That one came from this one right here. So this is a whole because it canceled with the top. The x minus 4 does not cancel with anything. So that means this value is going to be an asymptote. So that's how you tell if it's a whole or asymptote. All right, why don't you do the same thing on number 3. See if you can pause the video and try this one out on your own and see what you get. Okay, if you factored it out, you should have gotten what's listed here. Okay, you can see that in the denominator, the two places that it would be undefined would be at -3 and -2. Now you just got to figure out what type. The x plus 2's here do cancel. That led to this point. That means there's a whole there. This other one, x plus 3, does not cancel out. That makes this an asymptote. So check to see how you did. Those were the two values you should have came up with. All right, now the last problems, we're actually going to get into graphing some of these. Okay, we want to see what does one of these look like. So on this one, let's start the same way we've been doing. Does it factor? No. So where is this one going to be undefined? Take what's in the denominator, x minus 2, put it equal to 0. It looks like here that at x equals 2, it's undefined. Okay, what type of thing is that going to be? Well, since it doesn't, that x minus 2 does not cancel with the numerator, this looks like it's going to be an asymptote. Okay, and also on this table here, you see that conveniently 2 is left out. That's because if 2 was here, it would say undefined on there, and I'll show you that in a second. Okay, so we know we can come over here to the graph, and at 2, x equals 2, which would be right here, we're going to have this imaginary line we can put in that our graph is not going to ever touch. It's going to approach, but never touch. Now the rest of these we want to fill in on the table so we have some other points to graph. To do that, one way to do it is just to plug the numbers in. So if you say plug -2 in here, we could find what's f at -2. So you'd have -2 on top, put -2 in for the x on the bottom. You'd end up with -2 over -4, which is the same as 1/2. So 1/2 is what you get when you put -2 in there. So on here we know there's a point at -2/2. So that's a point on the graph. Now you could keep going like that. The quicker way though, especially if you have a graphing calculator, is just to type that equation in to your graphing window, and then you can pull up the table doing it that way. Much more efficient. So let's type that in. X divided by, now the denominator here has 2 terms in it. You need to put parentheses so that your calculator knows you want all that stuff in the denominator, and then close the parentheses up. All right, so if you hit graph, you should be able to take a sneak peek at what this looks like. Okay, and if we go table, you can get the table. So the table right here. Now mine's going by 0.5s. If we want it to go by 0.1s, you can change your table settings. So hit the second button window here, and we want it to start -3 is fine. My table change right now is at 1/2. I'm going to change that to 1 so that it's just going up by 1. So if I go back to my table, now you can see the same numbers here. So -2 is 1/2, same thing right here that we came up with. At -1, you get 0.33333. At 0, it is 0. At 1, it's -1. Notice on here, what does it say at 2? Error, because it's undefined at 2. At 3, it's 3. If you keep hitting the down button here, you can see some more values. So I'm going to keep going down here. There's some more. 4, it looks like it's 2. And at 5, it's 1.66. And then at 6, it's about 1.5. Okay, so now if we graph the rest of those points, we can kind of see what this graph is. So there's a point about there. There's a point right at 0, 0. 1, -1's a point. Then it jumps over to 3, 3's a point there. 4, 2. 5, 1.6 is maybe about there. 6, 1.5's there. So if you connect these, we know, now we hit this point, we know it keeps getting closer and closer, so now you just keep going closer and closer to that asymptote line. On this side, as we get closer to the line, we know it doesn't go through and it doesn't touch, so it must just keep going up like that. So that's the graph on this one. Okay, if you want to double check it, go back to your graph here, and you should see the same thing. It should look pretty similar. Yep, looks like ours is pretty much the same as that one. All right, let's try another one out. Number 5, they want us to graph this one out. So again, pull up, get a table, see what it looks like. Why don't you pause the video, try graphing this one out and see what it looks like. All right, let's see how you did. If you put the bottom equal to 0, you should see that's undefined at -1. Since it doesn't cancel with the top, that's going to be an asymptote. You can see on the graph there is a asymptote drawn at -1. Here's the values you should get in if you plug those x values in. And I got some points on here, so if you start connecting these now, you can see, okay, it's decreasing, which means it must keep decreasing closer and closer to that asymptote line. Here, as you connect these, it's increasing, so it must look like that on that side. So that's the graph of this one. All right, 2 more graphs here. On the next one, okay, start by factoring. Looks like there is some factoring on this one. So if we factor the top, that's a difference of squares, x plus 3, x minus 3. Okay, now we want to see where's this undefined. It's always going to be undefined wherever there's division by 0. So here, set the bottom, the denominator equals 0. Looks like at -3, it's going to be undefined. Now we got to see, is that a asymptote or is that a hole? Well, in this case, it looks like x plus 3 cancels with the top. That makes this a hole in the graph. And there is nothing else in the denominator, so this is going to be a, there's not going to be an asymptote in this one. Now, what's left over here after we canceled that out is x minus 3. So our graph on this one is f of x equals x minus 3. Or remember, f of x is the same as y equals x minus 3. We know what the graph of y equals x minus 3 looks like. It would be a graph that starts at -3. Our slope here is 1, or 1 over 1, so it'd be going up 1 over 1, up 1 over 1, up 1 over 1, or down 1, left 1. Okay, now normally then we would just connect all these and be done. However, we know there's a hole at -3, so there's one adjustment we need to make to our graph. We got to find where -3 is. Well, there's -1, -2, -3 is right here. If we follow that down to our graph, instead of a point, a closed-in point here, we need to adjust it. There's going to be a hole in our graph right there. So our graph does not go through that point. So it looks like it goes to that point, but there's an open circle there to indicate we don't have a value at x equals -3. So that's what the graph looks like for that one. All right, why don't you pause the video, try number 7, see if you can graph this one out with the hole. Okay, if you factored this one on the top, you get x plus 2, x minus 2. Setting the bottom equal to 0, you can see there is an undefined term at x equals 2, and because that x minus 2 does cancel with the top, it's not an asymptote, it's a hole. So there should be a hole in our graph at x equals 2. What's left in this graph then is x plus 2. So we need to graph what does f of x equals x plus 2 look like? Well, that's easy. Start at 2. Our slope here is 1, so up 1 over 1. And we should have a bunch of points like this. Okay, now be careful on yours. If all you did was connect these, you're wrong. There's one point, remember, that we don't have a value, and that's at 2. So wherever x equals 2 is here, looks like right here, if you follow that up to the graph, that point shouldn't be closed in. We should have a hole in the graph there. So make sure you got an open circle at that point. So that's what the graph looks like for this one. Okay, try some of the ones out now on your practice